Did you know Madeleine L'Engle's fiction predicted scientific discoveries? A look at A Wrinkle in Time, ahead on Science Goes to the Movies. Welcome to Science Goes to the Movies, a look at the stories of science and how they change our culture. I'm Faith Saley. Ava DuVernay is directing Madeleine L'Engle's 1962 classic story A Wrinkle in Time with Oprah Winfrey, Reese Witherspoon, and Mindy Kaling as Mrs. Which, Mrs. Whatsits, and Mrs. Who. And today we're going to look at the hard science in the original novel series. To do that, we will need both an astrophysicist and a cell biologist. And luckily, we have Matt O'Dowd, a CUNY astrophysicist and host of the very popular PBS series Spacetime, and Natasha Pavlova, a research fellow at Thompson Laboratory for Cancer Biology and Genetics at Memorial Sloan-Kettering Cancer Center. Thank you both for being here.
Thank you.
You're like you're like my fantasy football team of scientists. Thank you.
Wait.
You know, I think it's amazing that in 2 consecutive books, this woman went from the immensity of the universe to the minutia of the human cell. Was either of you influenced by Madeleine L'Engle?
Absolutely. Actually, my first encounter with Madeleine L'Engle's books, specifically A Wrinkle in Time, was in Russia in middle school. We read the first 2 chapters of A Wrinkle in Time for our English class, but we were only given the first 2 chapters, so I was left with quite a cliffhanger. And it only after like years later was when I finally read the whole book.
Why do you think you were given just the first 2 chapters?
Yeah, I don't know.
Is this a Cold War kind of edit? What was it?
Perhaps. I mean, some of the book is dealing, of course, with a little bit of a critique of a communist society, like the planet Camazotz, where everyone is supposed to be the same, and the society is permeated by fear of otherness or different, who's different, and yeah. So maybe it was part of that.
And what about you, Matt?
It was such
Did
a
they
long
let
time
Australian
ago.
children read this book?
They did. They allowed it.
In your English class?
You know, I read it very young, and so it exists in my mind as a bunch of almost, well, fantasy snippets that I'm sure shaped me. That and sort of that era of science fiction was about really unfiltered imagination, unrestrained symbolism. I mean, Madeleine L'Engle reminds me of people like C.S. Lewis or even Ursula Le Guin, just with being unshy about presenting your ideas in bold colours and really wild imagination. And I think it affected me in a good way. I think it I don't know, it expanded all of our minds. Yeah.
And these novels were written in the late 1960s and early 1970s. Right. So how much have we learned about the physics of galaxies since then? You know, since the days of shag haircuts and bell bottoms, is it still as groovy? Is it groovier?
It's so much. I mean, it was groovy then. It only gets groovier. I mean, I remember one thing in the book that one of the centaur people lived in a galaxy that I only later learned it's a famous galaxy. It's the Pinwheel Galaxy. Messier.
Which is a real galaxy?
It's a real galaxy, yeah. And although it hasn't been known that it was a galaxy for all this time, it's a beautiful pinwheel shape on the sky. It's 20 million light years away, so it's far. And that's where these centaur people live. But back in the 60s, we had only just begun to survey the universe, to map, you know, what is out there. Now, the furthest galaxy we know is really at the limit of what will ever be possible to see at many billions of light years away. And so understanding of the scale of the universe has expanded massively since then.
L'Engle's 1973 novel, A Wind in the Door, takes place in the mitochondria of this character, Charles Wallace. And I know that the discovery of mitochondria isn't, you know, attributable to one single scientist or pinpointable to an exact date. But was L'Engle's fictional writing right on the cutting edge of the science of her time?
Absolutely, and that's what's so amazing about the book. So yeah, the book came out in 1973, and it was like late 60s when the concept of mitochondrial disease was really put forward. And that's exactly from the first pages of the book we find out that the little boy, Charles Wallace, Meg's brother, is sick and he's not feeling well. He's out of breath easily. He gets tired from just walking across the garden. And his mother, a biologist, Mrs. Murray, she suspects that the mitochondria are not functioning well in Charles Wallace's cells.
Amazing.
And it's amazing.
It is
amazing research. And another very important concept in the mitochondrial field that also was put forth in the late 60s was the concept of the symbiosis, of the origin of mitochondria. The mitochondria didn't just form inside the cells, but they're actually remnants of ancient free-living bacteria that at some point they struck a partnership with bigger cells, and they kind of said, okay, we'll come and live inside you, and you'll protect us from the elements and give us nutrients, and instead we'll pay you in a sort of the energy. We'll give you back the energy that you could use for different processes. So that's what mitochondria do inside the cell. They participate in many, many different processes, but one that's very important is that they take nutrients that we ingest and the oxygen that we breathe, and they combine it and pass it through extremely complicated machinery and produce energy that cells can then use for other processes that are essential for our bodies, from moving our muscles and our hearts beating and our neurons firing.
And was L'Engle echoing this? Echoing these
I think, yeah.
investigations in the late 60s?
I think it's a very important concept in the book, is that little components need to work together in symbiosis in order to make the world possible.
Matt, in A Wrinkle in Time, the characters travel via tesseract.
Mm-hmm.
Per the story, characters use the tesseract to get themselves into the fifth dimension, creating a shortcut to move across the whole universe of space. Okay, so Matt, to me, fifth dimension is, of course, a killer 1970s soul band.
Right.
What is it to you in the field of physics?
Okay, so we have 3 dimensions of space and 1 dimension of time. So Einstein sort of told us integrating these two, so we have a 4-dimensional space-time. Adding 1 extra dimension, a 5th dimension of some sort, it potentially expands the realm of what's possible, of the way different parts of space can be connected. Mathematically, we can describe any number of dimensions. String theorists like to have 11 dimensions.
It goes to 11.
It goes all the way up to
theorists.
11.
Okay.
Exactly. But mathematically, it's arbitrary. In terms of physics, there's no evidence that there is a 5th dimension, really. But
this is so mind-bending for brains like mine. I mean, you guys can just talk about it. You could be like, I mean, when you're sitting playing poker with your physicist poker night, are you like, I think there's 7? I mean, how does anybody land on a number?
Well,
how many do you think there are?
As a non-string theorist, I never do that at poker.
Okay.
We mostly bag string theorists when we're. I mean, it's just.
We're going to have you back on the show to talk
with a string theorist.
So do you, Matt O'Dowd, think that there are 4 dimensions?
As far as we know what dimensions are, yeah. But, I mean, so the book talks about folding space, and it talks about, wrinkles in time, okay? So the idea that you can take the dimensions as they are and change their shape. In order to do that with even 3 dimensions, you sort of have to add to it an imaginary dimension, in a way, which you might think about as a 5th dimension. We think about space as being this sort of flat, sort of lattice structure thing that you can move through, up, down, sideways, back, forwards. But Einstein's general relativity tells us that space can be curved. So it could, straight lines don't stay straight, straight lines come together. In order to do that, you kind of have to invoke a 5th dimension in which that space can be curved. That was sort of what Madeleine was getting at, I think, a little bit.
You just said, as far as what we know dimensions are.
Yeah.
So, wait, what, we're not all on the same page about what dimensions are?
I don't think we really have any idea. what they are. What is space? What is time?
This is what I love about scientists, is how sanguine you look when you're like this. You're like, I don't think we have any idea what they are, and it doesn't haunt you. This is what you live for, right? Is the unknown.
It haunts, I would say, but it's a delightful question, and it may be one of the biggest ones. You know, what is it to have, you know, volume, and for one thing to be here, one thing to be there? What is it for 1 second to lead to the next second? Yeah, these are wonderful, but I don't think we know. I honestly think that we often talk around these ideas.
The characters in A Wrinkle in Time travel by sliding between dimensions. And Natasha, you've studied biology, obviously. What would it do to a body to slide between, you know, to slip between the third and second dimension?
Yeah, this is actually an interesting thought experiment, because on one hand you could offer some easy answers to that. Like you'd say a sphere would become a circle in the two-dimensional world, and the cube would become a square, and they would just like move about in this vast two-dimensional plane. But if we try to imagine how life would function and whether life would even exist in the second dimension, we would have to go deeper, all the way to molecular level. So imagine molecules that constitute life, all the chemical reactions, the molecules that participate in these reactions. Like if you remember the balls and sticks models, they are essentially three-dimensional, and you cannot just simply squash them in a two-dimensional space, because you'll break all the laws of physics and chemistry and how atoms are bond with each other. So we cannot just make a DNA molecule flat, or a protein flat, or a sugar molecule flat. So we would have to reinvent and reimagine the laws of everything from electromagnetism to quantum physics. And would gravity exist in the two-dimensional world?
Differently, yeah.
Differently.
But also the more dimensions you have, the more complexity is possible. A two-dimensional world is a very simple world, and life is about complexity. I mean, you need complexity to have chemistry, and chemistry to have life. And
all right, so bottom line, no traveling by Tesseract, you guys?
I don't know about that. I wouldn't go so far.
Okay.
There are thoughts.
All right.
There are ideas. So the idea that we have this three-dimensional space, but if you can have one extra dimension of space, then that's a dimension in which you can fold those three dimensions. And the classic idea is the analogy is in two dimensions you have, say, a sheet, okay, where every point on that sheet is, some part of the entire two-dimensional universe. But if you have a third dimension, up and down, then there's a way to bring two completely separate points together.
That's so romantic.
So that, I know, it's beautiful. But without that, this is what I was sort of getting at, the idea that with an extra spatial dimension, even if it's imaginary, then you can bring the real dimensions of points in the real three dimensions together. And these are real, I guess you would call them scientific ideas, things like wormholes or warp drives,
all the things we see in movies.
Exactly. But people have done the math, and it's with certain gigantic assumptions, some things are possible.
This is what's so cool about art meeting science, because when we do imagine what we think might be fiction and fantasy, it can overlap with real scientific thought. Right,
and so one of my favorite little pieces of what I think of as fan fiction was by a Mexican physicist named Miguel Alcubierre, who was a huge Star Trek fan and decided that it was possible to write down out of Einstein's equations of general relativity a metric that described the warp field. And he did so, and it should work with certain gigantic assumptions,
right,
like I said. That's sort of art meeting science, or art inspiring science.
So Matt, my art brain has kind of always assumed that the smaller numbered dimensions would be physically smaller. And does that make sense to a science brain? Or is there more real estate in a larger dimension?
I think that's a perfect analogy in a way. So we're in New York City. How did it start? Probably as a single room outpost when it was first settled, which you can analogize as a point-like thing. Okay, so 0 dimensions is a point. Eventually, that would have become a one-horse town. Okay, so when they needed more real estate, expand that single outpost, trading post, whatever, into a single strip. Okay, you've massively increased the real estate by adding 1 dimension. So that street is 1 dimension. When it starts to become a town, you turn it into a grid, so you make more streets. Okay, maybe 20 buildings become 20 times 20 buildings, 400 buildings. You now have a 2-dimensional square. But that's not enough real estate for us. So we add an extra dimension, we go up. Okay, so that 20 by 20 grid becomes 20 by 20 grid of high rises, and now you have a cube.
Yeah.
Yeah, that's 3 dimensions.
Yeah.
Real estate.
Yeah, I like that. That works for my brain. I got that.
Because you're a New Yorker.
Yes, exactly. In A Wind in the Door, L'Engle makes characters out of the parts of the mitochondria. She invents microscopic mouse-like creatures living symbiotically inside our cells called the furuncules. Now, Natasha, the furuncules are fictional, of course, but there are some really important engines working in our mitochondria. Can you describe who they are and what they do?
Exactly. Yeah, it's extremely fascinating because, mitochondria are indeed real, but Madeleine L'Engle invents kind of the further layer of complexity. And not only that furuncules are components of mitochondria, but they're actually sentient components. They have their own free will. And
which is unfortunately not true, right?
Unfortunately, it's not true. There's no evidence of furuncules.
So we have cells, and mitochondria is what inside a cell?
There are structures inside the cell. There could be hundreds of them in a single cell, and sometimes they fuse and form larger networks, and sometimes they kind of sit separately. They're usually portrayed as either round or elongated, just like we see on the screen at the moment. Yeah, and there is exquisitely complex machinery inside those mitochondria. And maybe furuncules are meant to represent that complex machinery that, you can see the mitochondria is filled with those pink and blue proteins over there. So these could be...
That's really what they look like?
Yeah, they're full of different enzymes that produce different building blocks for the cell, and also dismantle some of the nutrients to make... to produce energy from them.
So are they, would you call them the engines of a cell, mitochondria?
Yeah, it's like an energy station.
Okay. I think I remember when I was a kid learning like MIGHT, right? Like MIGHT, mitochondria would be like the muscles of the cell.
Yeah, and actually, since Matt brought up Star Trek references, I see a Star Trek reference, and I'll raise you a Star Wars reference.
Thank you, please. I think I know where this is going.
If you remember, I think it was only in the prequels, they talk about midichlorians, the midichlorian count in the blood of Anakin Skywalker, the Jedi. And they find the midichlorian count is off the chart. So midichlorian kind of sounds like mitochondria, and I think in one of the interviews, George Lucas actually admitted that the midichlorians that he had invented are supposed to be superpowered mitochondria.
It was only in the first prequel, by the way, because there was such a massive fan backlash against trying to science up the Force that...
You guys are the most fabulous, best-looking geeks I've ever encountered in my life. This is like...
You are too, Faith.
Oh, well, thank you. This is like, these are the moments I live for. Wait, so was the suggestion that Jedi, who are kind of like almost a superior kind of person, have extra mitochondrial power?
Extra mitochondrial power, exactly.
And what would that actually do if you had too many mitochondria? Would you just be peppy?
Yeah, what would it mean?
Yeah, I don't think that such condition is described. We obviously have mitochondrial diseases when mitochondria are not functioning well.
Can we up our mitochondrial levels?
You could make them work better. Exercise makes them work better because they adapt to increased energy demand in our muscles. So
juicing. I mean, juicing. You have to juice for everything, right? L'Engle was a Smith grad and a classmate of Betty Friedan. And in the whole of the universe, there were no characters like Meg Murray before Meg Murray. And L'Engle's Murray is an awkward, angry, smart girl. And Madeleine L'Engle lets her be that way. Natasha, how do you think seeing truly human, female, flawed, and inspiring characters, how do you think Or do you think that matters in the scientific community?
I think it's so important, and it's been important in the 70s, and it's more important than ever right now. So yeah, we have a female character in the book who is, it's like we talked about dimensions before. She's not one-dimensional, she's not two-dimensional. She has all these sides to her. On one hand, she's so kind and she's so protective of her family. She's fiercely protective of her little brother. In both books, she saves his life by just going bravely and confronting the highest evil she encounters. And I think there's a very important interaction in A Wrinkle in Time, when I believe it's Mrs. Watsit, right before sending them to the planet Kamazots, she says that I'm going to highlight your biggest strengths. And your biggest strength, Meg, are your faults. So what teachers and the principal are saying, oh, Meg, you should tone it down, don't be as abrasive, don't be as contrarian. But Mrs. Watson says this is your strength. And interestingly, to Calvin, the boy who also goes on the adventure to them, she says that, Calvin, your biggest gift is communication. So it's interesting that the gender expectations are a little bit, they're flipped.
That makes me so emotional. It makes me think of all the girls throughout history who needed that message. And still need that message.
Exactly. Yeah. Sometimes you cannot win by just asking nicely. Sometimes you have to put your foot down. And
have you had those experiences?
Yeah, certainly.
Matt, given the world's current, let's say, troubling relationship with facts, how important is society's perception of who and what is a scientist now?
This is perhaps the great battle of anyone who tries to communicate science or is interested in science education. I think it almost feels like a war sometimes, you know. I mean, you have the extremes, okay, and let's say the political spectrum has its extreme ends. On the right, you might have science denialism that comes from religious fundamentalism or, you know, excessive adherence to the idea that market forces are benevolence.
Economic self-interest, yeah.
Exactly, over scientific evidence to the contrary. But even on the far left, you have, you know, particularly loopy New Ageism. You have...
like anti-vaxxers, too.
Exactly. Right? So you have conspiracy on either side. You also have this kind of slightly unhinged postmodernist idea that science is a patriarchal Western paradigm that can be discarded. But I feel like the middle is where you need to look, really. But even in the middle, on one side, I think most people trust scientists. And, you know, even like science, or at least like what science brings. But this new era in which we're bombarded with alternative facts leads to an effect which I think is actually quite deliberate. The effect is that the average person trying to understand what is happening in the world is bombarded by just so much nonsense,
right,
along with the real facts.
How do you filter?
Exactly.
And when you do filter, are you still left with what's true?
And, you know, I think a lot of people have the capacity at some level to filter, and even not trusting the people who are presenting fake science because they're clearly partisan and maybe even clearly lying. It doesn't matter in the end because you're bombarded with so much that you just run out of the energy to critically analyze. You get fact fatigue and you just end up thinking, well, I guess we can't really know. The problem's too complex, you know. And so I think this is this deliberate attempt to turn what is strong scientific consensus into ambiguity, at which point it doesn't matter if you're lying, and if you're caught lying, you've won. And so, you know, the answer is, it's extremely important for people just to have kind of a basic level of scientific literacy, so they know what science looks like, and they know what expert testimony looks like, without having to be overwhelmed by it.
We need you both to be as fierce, relentlessly fierce as Meg Murray at all times.
Yeah, it's a worthy battle for sure.
What do you guys think about hard scientific concepts presented as fictions?
Would you like to go first? I have an opinion, but
sure,
please.
yeah. I think it's extremely important. So first of all, like we've discussed already, the concepts that are presented in Madeleine L'Engle's book are very accurate for the time. And I'm sure they've inspired now generations of children to learn more about different dimensions, as well as learn more about the inner workings of the cells. And I'm sure many a child were disappointed that farandulae are not really inside our mitochondria. However, I think it's very important to introduce children to the concept of science, that it's not something that's just written in textbooks, something that you're supposed to memorize, then take a test, and then forget. But that science is something that's done by people, that's living and developing every day. And that's why I think it's so important that Meg and Charles Wallace's parents are scientists, both of them. And so I think it's important to remember the human component of science.
Yeah, and having scientific ways of looking at the world just suffuse our fiction, particularly fiction for children, teaches kids that thinking about the world scientifically is normal and natural, and it's not just for nerds or experts. It's not,
or super brainy people.
no, it's for everyone.
Yeah.
And this is, you know, we can all essentially be scientists in a way.
Every kid's a scientist.
Normalizing it,
right?
is, yeah, absolutely. I mean, kids are curious naturally. You have to kind of beat that out of them.
Yeah. Natasha and Matt, you have wrinkled and made time fly. Thank you so much for being here.
So much fun, thanks.
Yeah, thank you for having us.
Whatever we can't fit into this half hour, we'll share on our Science Goes to the Movies Facebook page. And if you want to watch past episodes, check us out at www.cuny.tv under the Science tab, or download our app to keep up with everything related to Science Goes to the Movies all in one place.